Welcome everyone, my name is Schneider von Deimling from Kiel University, and I want to talk about ambiguous multibeam seafloor bathymetry and backscatter measurements using a broad frequency range. When you work in marine science and business, sooner or later you come in touch with mud. And don't let the mud fool you, because it can produce some peculiar acoustic phenomenon. Let's have a look at an echogram recorded with 100 kilohertz. Down here, and what you see is, well, the water column, and you might think here you see a prominent reflector, the seabed, and further below you get a multiple. Well, we stayed on this position for some hours and waited for a tidal wave kicking in. And let's have a look how the echogram changes over time. Actually, the former believed seabed is a fluid mud package sitting on the real seabed, and it's being broken up, getting to a rough surface, which lets the sound penetrate better, and therefore you can finally image on the seafloor. I'm showing this because imagine you have a multi-beam system working with a bottom detection algorithm. It's very tough for such an algorithm to get the seabed mapping right in this situation. Well, what is mud? Mud is actually a mixture between clay, silt, and sand, and it has some acoustic specific behavior. Like usually it has a pretty low roughness. It's fine grained. It's often layered and has very low acoustic attenuation compared to sand or rock. And also it can form what we call a slow reflector. That was observed by Hamilton already in the 70s and later described in the famous textbook by Jackson and Richardson. And it produces kind of a sound channel in very soft sediments. Well, mud occurs all over the globe, often in coastal inlets, protected bays, but it's also very often and very common in the deep sea, as shown by Markus Diesing in this nice map. So very often you do face muddy sediments with your acoustic measurements. Let's have a look at a table. This is presented in the Backscatter Working Group report and taken from the APL labs. Now let's have a look at some acoustic properties like density, P-wave velocity, or absorption of the sound of clay, fine silt, medium silt, and so forth. And now I compare this with some belly fat, human belly fat. Why this? I show you in a second. Actually, belly fat properties is quite similar to medium silt. That's how it is. And why mentioning this? Because in medical ultrasound, more than 1000 kilohertz are being used. And you get, in this case, at least 10 centimeters penetration. So when using multi-beam echosounders in between typically 12 and 400 kilohertz, expect decimeters to meters penetration in mud. Over the past 15 years or so, we have been using a lot of different multi-beam echosounders from Kongsberg brand ELAC, that's a German manufacturer sitting right next to us. Higher frequency Kongsberg systems. We have our own NORBIT system, and we use quite a lot parametric sub-bottom profiler like Parasound systems or Inoma. Here you see a picture of the dimensions of the different transducers, of course, depending on the frequency. Now let's go into the field, into the Baltic Sea. This is actually not an ocean, but a drowned glacial landform. And within the basins, you do have accumulation of Holocene organic rich mud. Here's another acoustic record of such a mud setting overlaying a glacial till, and you see the mud is often very nicely laminated or layered. And when it exceeds a certain thickness, often you get methanogenic shallow gas, not depositions, but shallow gas pockets, I would say. Please note, it's not a scenario where the gas migrates from below, but it's being produced in situ. Overall here, the mud is as thick as 12 meters, has low roughness, low density, and sometimes behaves actually as a slow reflector with angles of intromissions. Well, when we cross such an interface with 95 kilohertz multi-beam, we do get actually the true seabed surface. However, we did experiments with 12 kilohertz in this geological situation and could promote subbottom detection of the shallow gas fronts and the glacial till. So with 12 kilohertz, you kind of get the possibility to map subsurface structures with multibeam. Finally, we validate our measurements usually by coring. Let's have a look at almost the same location with another subbottom profile taken with the parasound system, showing basically the same geological situation. We do have shallow gas with acoustic blanking and turbidity. We do have the glacial landform, and here overlain by Holocene mud. And the difference in between this interface and the seabed surface is 12 meters. Now, we ran 12 kilohertz multibeam, and what we get is the top of the glacial landform, not the seafloor, and the top of the shallow gas. Now have a look at the 3D perspective view of the 12 kilohertz multibeam measurements. The color codes originate from the backscatter, and you do see with the perspective view a little bit of a kink in the surface, which is not a kink in the seafloor, but has to do with the transition from shallow gas to non-shallow gas. Overlaying literally on top, we do have the 95 kilohertz multibeam record that shows the true seafloor. Now, also interesting is the behavior of the angular response in these two domains. In the red, taken here, we do see an ARC response, which is more or less totally flat. This has to do with the omnidirectional scattering of gas bubbles, while in the blue, the glacial till rather shows a typical angular response decay for a sedimentary seafloor. So overall, note that we do have a multibeam penetration of at least 12 meters in this case. How reliable can we map subsurface structures with using two different frequencies? For this reason, I plotted the layer depths that we picked in the subbottom profile on the x-axis and plot the difference bathymetry, so to say, of 95 and 12 kilohertz, and we do see a pretty nice linear correlation in between gas and Holocene base. Now, how can we visualize subsurface objects more convincingly, so to say? There's a little easy trick. Gas usually kicks in very suddenly, producing a super strong slope. And when you apply a simple slope filter, which I did in MBES systems, then you can actually visualize gas pockets in basins like I did here. The geological interpretation across this profile would follow with, we have outcropping glacial till, then we enter with the sound the real seafloor and penetrate through mud, still imaging the glacial landform underneath the actual seafloor. And once a critical thickness of the mud is exceeded, shallow gas kicks in and the bottom detection jumps to the top of the shallow gas front. All right, taking a deep sea sound of 12 kilohertz everywhere is not that handy because the transducer is huge. How would that approach apply with a mobile transducer? We have one with 50 kilohertz manufactured by ELAC from Kiel in Germany, and we actually succeeded to do the same thing, mapping a subsurface shallow gas with this echosounder and with a penetration depth into the seafloor of 2 meters, showing patches of shallow gas. However, it needs to be noted that this business is very depth dependent, and you cannot expect that it works the same everywhere. Here's a nice example of acoustic turbidity on one location with 4 kilohertz, where we see some significant acoustic blanking due to bubbles, where in turn, using a higher frequency, we are able to penetrate through the bubbles and through the mud. This has to do with the nonlinear behavior of gas bubble backscattering, which is very size, frequency, and depth dependent. And we expect similar complex, let's say, multispectral responses for any kind of compressible fluids may it be methane, oxygen, buried fish with swim bladder, or also other structures that do show a complex backscattering behavior. You can map out some peculiar looking seabed features. This is not a hidden city or something like this. It's simply an artifact caused by shallow gas in mud when you survey with multibeam around outcropping scenes. Now, what about 400 kilohertz and shallow water multibeam systems? Wouldn't you assume that with those you actually get the real seafloor? Here's an image of a famous groundwater pockmark site here in the Kiel Bay. And I used to think there's a hiding place for submarines that are operating close by in the muddy seafloors. But we learned that actually what you see here is also penetration effect. And part also of the pockmarks, it's more an acoustic penetration effect than showing the real seafloor. How does the backscatter plot in this area? That was taken with EM2040C, and we had overlain the nice snippet imagery across this area. And when you look closely, I plot together the bathymetry in black, showing pockmarks depressions, and the backscatter of the multibeam system on the same profile. And you do see that each time we enter a pockmark, the backscatter actually increases. Geologically, this doesn't make much sense because it's a sediment trap, and you would expect that it traps finer material with less backscatter. The reason, once again, is acoustic penetration. Even with 400 kilohertz, we think the acoustic penetration leads to picking up signals from 10 to 20 centimeters in this muddy sea floors. And we again use a subbottom profiler to look at the subsurface features where you can see small pockets of gas. And when you integrate the acoustic energy of the subbottom profiler between 20 and 50 centimeters, it correlates to the multibeam data. So quite astonishing penetration and catch up of signals by volume scattering underneath, even with 400 kilohertz. This topic has also some very practical applications, especially in harbors. You might have heard about fluid mud and the problem that harbors needs to get rid of fluid mud, and the question how navigatable is fluid mud for ships. There's no consensus where the seafloor begins. Some harbors define it as 1.2 tons per cubic meter. Other harbors simply say, well, for us, the seafloor is where a 24 kilohertz system detects the seafloor. However, this is of course dependent on the bottom detection algorithm implementation. Anyhow, there is ongoing research on this. Some of you might have seen those phenomena in multibeam water column data. But not only in water column data you would see the imprints of fluid mud, but there are also systems that try to actually sense two layers, the top of the fluid mud and the actual real seafloor. Here's an example from NORBIT operating with 80 to 370 kilohertz, and you do see two kind of realities. The first one showing the bathymetry, and here with another frequency, the bathymetry is significantly deeper. Difference is almost one meter here. There are more developments ongoing. We are currently in a research project with Fraunhofer, who built a multibeam based with 15, 24, 36 kilohertz, especially for the demands in fluid mud and harbors measurements. And also with, for instance, there's a NORBIT system operating between 80 and 400 kilohertz as shown on the left. Here's another example how different the reality can look like when considering penetration effects and also kind of exploiting that for the potential to map two different kind of layers and seafloors, so to say. Well, conclusion and outlook for this: expect DC meters to meters penetration when using multibeam in soft sediments. It's more common than you might think. Shallow gas is a special case, but it occurs in many places, harbors, coastal areas, and so forth. And it can really deteriorate your backscatter interpretations or so, be aware that you can also map those in 2D with multibeam systems, and which other subsurface properties and features can be actually mapped with multibeam systems. There's a huge field of research. That's also what is being handled in the backscattering working group. There's a branch about multispectral multibeam acoustics, and there's a lot to come. Personally, we work at the moment at sensing buried life in the seabed as one possibility what you can do with multibeam systems. All right, so thank you very much for your attention. I hope you liked the presentation and have a good day.